So I'm going to take a whole sick day and take care of things. Okay. On to gases. Okay, so this stuff, this Unit 5 stuff will be on your exam, okay, but there will be no official Unit 5 exam set alone. So you'll see gas problems on your final. That's what I meant to say, on your final exam. So when you picture a gas, a lot of stuff falls into place with regard to this. And I'll just kind of put up a little box, and in that box, okay, these are cute little gas particles bouncing around. Okay, I'll go ahead and kind of give them some motion, bouncing against the sides of their container. So one of the things is we could take that container and make it smaller. So gases are what we say compressible. When you buy liquid gas or gas that's been liquefied, you are buying compressed gas. Basically, it's been forced to form those intermolecular bonds. Gases, given their choice, they will go ahead and fill every little cranny, crook and cranny of the container you put them in. They don't have to be a square container. It's kind of fun. Density is a ratio of mass to volume. So if you can actually compress it, okay, then you're changing the volume even though the mass stays the same. So the density is kind of a moving target with regard to gases. So the densities, they're very sparse compared to liquid and solid. This one kind of makes sense. The fact that they're jumping all around, if you have, and this is kind of neat, if you have a box that has oxygen gas molecules and nitrogen gas molecules, it's not like the nitrogen's going to go over here and the oxygen's going to go over here. In fact, nitrogen is a little more dense. Oxygen is a little more dense than nitrogen. It's not like they're going to go form two layers. They're bouncing all around. They're going to go ahead and make a mixture, specifically a homogeneous mixture. The other thing is the P term that we're going to talk about when we talk about gases. It comes from the fact that those gases have a lot of kinetic energy and they're bouncing on the edges of their container, or the container that's holding them. Okay, so they exert a pressure on the walls of the container that's confining them. It's like they have a little personality. So we're kind of building up to the ideal gas law equation, and I'm hoping to get to that today. Okay, but I'll go ahead and I draw a lot of boxes just because that's how I kind of see it. An ugly box, I know, they're similar to my beakers earlier in the semester. Okay, but so gases are bouncing around in there, and if we want to clearly say the condition of that gas, we need to give these four variables: pressure, volume, N for the number of moles, and T for the temperature that gas is banging around in. Okay. So I'll go ahead and kind of cut to the chase. Later on, coming up soon, like I said, hopefully today, you know that there's one equation that can link all four of those variables, and we throw in a constant. PV is equal to nRT. Okay, that actually is called the ideal gas law equation. Gas law equation. Okay. So you need those four things. Notice what you don't need. I love this. You don't need the identity of the gas. Identity, question mark. You really don't care. That's one of the things I love. It's like carbon dioxide and I don't know if it picks the water, gas. All gases behave the same according to this equation down here. Okay, so the whole gas particles have a lot of kinetic energy and are exerting pressure on the side of their container. Okay, pressure actually, whether it's a gas particle exerting it or not, pressure can be thought of as force per given amount of area. Okay, so this is kind of a neat sort of thought. Both of these cylinders weigh the same. They have the same mass. Okay, same mass. Okay, so actually they have the same mass and they're both here on Earth, so actually they have the same weight, and weight is a force. So this is all to say they are exerting the same force downward. But if you look at the areas, okay, the fact that actually this area is smaller, okay, this means that this is a greater pressure. P is higher. Yeah, and it's intuitive because you think you have a certain amount of force, which actually is related to the mass or the weight of those objects. And if it's distributed on a larger area, like this pink one, you know, the pressure is going to be less. It just is. Okay. So force then actually can be broken down according to Newton as mass times acceleration. And when we talk about force, a fundamental unit of force in physics actually is the Newton. They must have named it after him because they loved him. Okay. And Newton can be broken down into units that we're familiar with. 1 Newton is equal to 1 kilogram meter per second squared. That's force. Okay. So if pressure is force per area, and the fundamental unit of force is a Newton, and the fundamental unit of length in the metric system is the meter, area is meter squared. So a fundamental unit of pressure would be 1 Newton per meter squared. And actually, one of the ways of talking about pressure is pascals, and so PA stands for pascals. We in chemistry aren't going to use much with pascals, but it's a good unit. So I'll show you which units of pressure we really will see. One of the units of pressure that you're going to see is the atmosphere. And you don't have to memorize these equivalencies. Actually, I say that, and yet there is one that you're going to want to memorize. The equivalent pressures that you're going to want to know is this one right up here. Actually, in homework problems, the R, the ideal gas law constant that I use, R, actually, you're going to want your pressure in units of atmospheres. So if your pressure is given in units of millimeters of mercury, which sometimes it is, you're going to have to convert. And so you're going to want to convert that to memory. Notice that's an exact relationship, though there's no uncertainty there. The bar, actually, we ran into the bar earlier. Remember we said that standard pressure for thermodynamic problems is 1 bar, approximately equal to 1 atmosphere. This is kind of a fun one down here, okay? When you go to inflate your tires, okay, you inflate your tires according to a certain PSI. That's pounds per square inch. That's what that is. Isn't that kind of fun? So that first one with an arrow, commit that to memory. For your lab that we're going to do, I'm pretty sure you're going to want to know what a torr is. Okay, so these are all units of force per area, or units of pressure. All right. So this is kind of neat. We have basically water. That fluid, well, I assume it's blue-colored water probably, has reached, been allowed to kind of settle down. And notice that in these assortment of tubes, they have all reached the same common level. Okay. So this says that the liquid pressure is proportional to the density, okay, and the column. So these are all equal pressures, liquid pressures. Speaking of liquid pressures, one of the ways, and we don't do this in the lab, when I need the pressure of the atmosphere in the lab, I use the internet. But we do have a couple of mercury barometers in the lab. And what a mercury barometer does is it's great for measuring the pressure of the atmosphere. Okay, so notice that here we have whatever is in the atmosphere, whatever is in the room where your mercury barometer is, has these particles of mostly nitrogen, about 80% N2 and about 20% O2. They are creating a pressure in all directions. One of the directions they're creating a pressure in is on the open pan of liquid mercury down there. So what happens then is this liquid mercury can have a choice. It can actually, I should say the liquid mercury of interest is here in this column that is closed at the top. Closed. So that liquid mercury can kind of bob up and down depending upon or responding to whatever the atmosphere is doing. So the greater the atmospheric pressure, the more it's going to shove that liquid mercury up into that column, that glass column. So these are all, well, they aren't all, right? I'll kind of go from left to right. The thing that makes the first one wrong, well, I'm saying wrong, but if you're trying to make it a mercury barometer, notice that it's open at one end. That's not going to work. Like you saw on the previous slide, basically it was mercury barometers. The glass tube part was prepared by first creating a vacuum and then inverting the open end into an open pan of liquid mercury. Who wants to have that job? I used to play with liquid mercury. And then here, B and C actually are basically the same. The top is closed, and what you're seeing is the pressure of the atmosphere, okay, is causing the liquid mercury to rise to the same place. And D, that's a failure, isn't it? Because basically you didn't leave your glass tube long enough. The thing about it, especially as we kind of have these stormy days, if you are a weather buff, you know that if they say that the barometric pressure is falling, okay, then you can expect clouds or storms. And a lot of times they will give that barometric pressure in terms of inches. Specifically, for instance, a high pressure might be 30 inches, and it doesn't take much to be a low pressure, so you could have like 29.5 inches. And I'm here to tell you that those inches, is basically mercury being shoved up a tube. That's the way the weather people do it. Well, back to the lab. Now I was trying to think which chemistry class I use something like this. Not in inorganic chemistry, which is what you're in, or general chemistry. Not even organic chemistry, but maybe advanced inorganic chemistry. Sometimes you actually have something interesting going on in a vessel. That's your reaction flask, okay? And you go ahead and just kind of like when you guys did your titrations, this actually is a stopcock. And notice that the stopcock is parallel with the glass tubing. So actually this is open, okay? So this is a way then, by the way, this right here is liquid mercury, okay? So that liquid mercury can kind of go back and forth in that little U-tube. Okay, it's U-tube? Get it? So for instance then, if our gas has a pressure that's greater than the pressure of the atmosphere, by the way, I hope we're okay with this, that anytime you see, for instance, pressure sub BAR, that's the barometric pressure. That is the pressure of the atmosphere. That's atmospheric pressure. I don't know why but that's just what it is. So in this case, do you see where what's ever in our flask, that, like this says down here, what's in the flask is greater than the atmospheric pressure. How do we know that? Because the liquid mercury has gone up that way. It's possible then, one more scenario, is that what's ever happening in our flask, maybe it's consuming the gas. Okay, maybe gas is a reactant and being used up. And in this case, you see actually that the pressure of the gas is less than, this actually is less than the barometric pressure. Again, barometric pressure is just the pressure of the atmosphere. So that's how we can use liquid mercury to actually measure those things. Okay. So the box a little bit ago, we said 4 things you need to characterize a gas fully. You don't have to include its identity, but P, V, N, and T. So what I want to do now, and actually kind of pulling through Boyle's, Charles, and Avogadro's law, is to look at a pair of them Okay, take two at a time, and we're not going to confound it. We want to keep the other two constant. So in this case, I just want to isolate pressure and temperature, and I want to hold volume, the volume of the box or whatever, and the number of moles of gas in the container. I want to hold those constant. And these are very practical things. So these two, pressure and temperature, for all gases are what we say directly proportional. Okay, that means a direct relationship means as one goes up, the other goes up. So a really good example is that if you have, I usually say like, something practical, like you buy a balloon at the store, and let's say it's a cold day out there, and so you put your balloon in your car, okay, and the lady at the store filled it up just great, but you come out to your balloon later, and actually it's so cold that the gas particles in your balloon have slowed down. So basically, you have basically the same volume, and you have the same number of moles of gas because they didn't get out of your balloon, but you don't have the same pressure. Okay, why? The temperature went down, the pressure went down. Okay, temperature goes up, pressure goes up. And to me, if you kind of think of temperature being related to the kinetic energy of the particles, it makes sense. Again, this is holding the volume the same and the number of moles the same. Okay, so we use the symbol, that looks like an infinity sign with a bite out of it. That actually is the symbol for proportional. So we say pressure is proportional to temperature. Oh, really? Wrong mouse.
If the temperature of a constant volume of gas is increased, the molecules of the gas move faster, and each collision exerts a greater force on the walls of the container. In addition, because the molecules move faster, the number of collisions between gas molecules and the container walls increases, and therefore, so does gas pressure.
So the direct relationship between pressure and temperature. I usually think you monkey with the temperature and the pressure is also affected. Okay, here's pressure and number of moles. And so not so surprising, they are also proportional. And to me, a good thing is like if you're blowing up a balloon and you're almost to like the volume the balloon can hold, right? Okay, but let's just say you go ahead and blow more into it. You blowing into it is increasing N, okay? So with each breath you blow into it, you're increasing N, and actually can you almost feel the tautness, the pressure increasing inside the balloon. So increasing N increases the pressure. It just does, okay? Holding the volume and the temperature the same. So they are directly proportional. If you decrease the number of moles, you decrease the pressure. There again, I figure you can monkey with the number of moles, and then the pressure is affected.
If the number of gas molecules in a container is doubled, with no change in the temperature or volume, the number of collisions between gas molecules and the container walls doubles, which translates into a doubling of pressure.
I like it when things seem reasonable. Well, this is our first inversely or indirectly related pair of variables. So volume and pressure have the reverse relationship. And to show that they are inversely related, actually, we can say volume is proportional to 1 over pressure. Same thing. Okay, so it's proportional to 1 over P. And I'm going to show you some examples here, but an example would be you take your balloon, okay, that has a certain volume, okay, and you're going to keep the number of moles in there and you're not going to monkey with the temperature. If you take your volume and you squeeze your balloon down, okay, what's going to happen to your pressure? So you are decreasing volume and increases pressure. Okay, decreasing volume, increasing pressure. We could do another thing where it's already just really compacted. You go ahead and if you increase the volume, you're going to decrease the pressure. Increase the volume, decrease the pressure. So they have an inverse relationship. So here's a little animation for that.
If the volume of a container of gas is reduced by half, but the amount of gas remains fixed, more collisions will occur between gas molecules and the container walls in a given time, leading to an increase in the force exerted on those walls.
So we've taken one of the 4 variables and compared it to the other 3 variables, holding the 2 variables we weren't interested in constant. Okay? Thou shalt not confound what you're looking at, and that's kind of what we tried to do. All right, so to kind of summarize, and I think you guys don't necessarily have this, but we first said that pressure and temperature are directly proportional. Makes sense. You heat something up and you don't change the volume and number of moles. Actually, you're going to increase the pressure. Pressure and number of moles are directly proportional. Actually, we said this one down here. We said pressure and volume are inversely proportional. And actually, there's 2 ways to say that. Well, it's funny. I'll go ahead and put all these up here. I added, if you want to add to the slide next to that, you can. Because these are famous guys, and they're all guys about gases. Well, I tease that behind each one of these guys is probably a woman saying, hey, did you try these? No, I'm just kidding. But all that these folks have done, and they did some great work actually before we really understood as much about matter as we know, but is Boyles looked at the relationship between volume and pressure, and Charles looked at the relationship between volume and temperature, and Avogadro's number, looked at the relationship between volume and number of moles. Okay, so you can already kind of see how they're related. And here in a minute, we're actually going to combine these 3 proportionalities with volume on one side and kind of make something, come up with the ideal gas law, okay, the PV equals nRT. So before we kind of dive into those 3 laws, Charles' law, Boyle's law, Charles' law, and Avogadro's law, they all relate to gases as gases are behaving ideally. It's funny because is anything ever ideal? No. Okay. So what that means, and I was thinking about this in my office, if I were to go ahead and to draw one of my famous boxes that's containing gas particles in there, okay? So here's my gas particles. According to our first assumption, okay, there are no intermolecular forces. I like to say that each gas particle doesn't care that the other gas particle's there. They're just like, whatever. I'm not going to form any intermolecular bonds with you. The other one is kind of interesting. It says basically the size of the gas particles themselves is 0. It's negligible relative to the container it's running around in, okay? Which is kind of strange. So those are 2 assumptions. And actually, do I say it on the next slide? These work pretty well at high temperatures and low pressures. Okay. Thank you. These work pretty well as long as you have relatively low pressures. Oops, sorry. Yeah, relatively low densities, I guess I should say. Low densities. That means that you're not shoving them together, and high temperatures. That means they have a lot of kinetic energies. All right. So gases are behaving ideally. There are basically no intermolecular bonds, and they have no volume. So let's look at what Boyle said. And he said that volume and pressure are inversely related. And actually, we already said that a minute ago, that as you inverse relationship like this, they're proportional to the inverse of 1. Inverse relationship means as one goes up, the other goes down. Is this where I see this? Ah. Now, getting you ready for the ideal gas law equation. Anytime you have a proportionality statement like that, V is proportional to 1 over P, it's cool, and they do it all the time, to replace that general proportionality symbol with an equal sign if you introduce a constant. So we're saying, all right, in fact, I wish I'd done that. I'll show you what I mean. I wish there was a step between that. So this actually is replaced with an equal sign, some constant K, 1 over P. Do you see where we can rearrange that? Now, to work ideal gas law problems, if you've done them before, you know that you have to keep a check on your algebra. So you know that, what's snowing? Lots. You know that if we want to rearrange that, getting K all the way by itself, I'm not a math person, we can actually multiply both sides by P. That's kind of how I think of it. And in doing so, those go away, and we end up with that. Does that make sense? Okay, so you can do that with any relationship that has a proportionality sign. Okay, so as pressure goes up, check this out. As pressure, for instance, goes up, we'll pick on pressure, volume needs to go down because multiplied together they equal some constant. Literally, multiplied together they equal some constant. And vice versa. So here's a figure from your textbook, that relates a couple of pressures and a couple of volumes. Now notice, and we're assuming that the number of moles that's being contained in that little, this is it's like a movable piston sort of thing. And this is the gas of interest, that kind of brown looking stuff, okay? So the more weights you have on the movable piston, then the more pressure you have. Actually, the number of weights is an indication of pressure. So notice in scenario 2, we have a higher pressure and we have a smaller volume. In situation 1, we have a lower pressure because it only has 1 weight and a higher volume. Okay, so they are inversely related. Okay, saying that again, this is less, this is more. Sound like a commercial. Okay. This is more, okay, this is less, related to each other. So then what you can do, and scientists like to do this all the time, is go ahead and plot those 2 points. Okay, so here is a plot of volume versus pressure. It has what? We'd say a negative slope. Okay? That all works. So when we, for instance, use a bike tire, okay, the pressure part comes into, you're applying the force here, okay? And then the volume that you're decreasing is the cylinder kind of gas. Okay, so as he pushes down, he actually is making this volume smaller and smaller and smaller, okay, which is increasing, decreased volume, increased pressure. And his hope is to go ahead and jack up his bicycle tire so he can go for a ride. So I have a few slides here with this sort of scenario. Now, one of the problems we run into in chemistry lab, gas labs, I think, is what is our gas of interest. And so your gas of interest is right, it's adorable. Okay, that is your gas of interest. So basically, for the next few slides, you're going to see, the next slide, you're going to see that basically a stopper is placed over this. This looks like an Erlenmeyer flask, and it is an E-flask. It is an Erlenmeyer flask. But actually, it's thicker than usual, so it can be pressurized, and it's an Erlenmeyer flask with a side arm. So in this scenario, then, you see the lid put on it, okay? And I'm going to go back to see if, yeah. Okay, so look at our volume of interest. And the next caption is, we went ahead and through the sidearm took our bicycle pump and applied pressure. So we increase pressure in this chamber, increases pressure on the plunger, decreases volume. Increase pressure, decrease volume. That's it. And if you compare the previous slide with this slide, increasing pressure, go ahead and decreasing the volume. Where's the air of interest? This one right here. Okay. I like this one. This one's adorable too. Okay. So actually in our lab, it's not too hard, and you can do this with vacuum cleaners. You know, well, vacuum cleaners are good with sucking. Okay. In our lab, actually, we can do this with our water hoses. But if you draw a vacuum, then instead of increasing pressure, if you decrease the pressure by drawing a vacuum, check out these marshmallows. So we're decreasing pressure, increase volume. Are those not adorable? Okay, so this is drawing a vacuum on it. So the air that's trapped inside those marshmallows says, I'm going to stay in this marshmallow, but now that I'm at a reduced pressure, I've lowered my pressure, I'm going to increase my volume. Then I like this one too. Go ahead and instead now of drawing a vacuum, put back on your tire pump. Okay. So instead of normal marshmallows at a normal pressure, okay, you increase the pressure. Increase the pressure so you decrease the volume. It's just wonderful. Okay. So here are a series of slides. Now, in order to have this make sense, I want to point out that we have mass here, and actually this is basically the pressure, because if you look at what the mass is, we're going to add mass to, you're going to see in the next few slides, we're going to add mass to that little cup there. The air of interest, again, right there. Okay. So we're going to add mass, increasing pressure on that syringe. Now, instead of volume, though, notice what's plotted along the y-axis is the inverse, or 1 over volume. So check this out. So with nothing in the cup, okay, we have 0 mass, and again, mass can be directly related to pressure. And the volume we have here is 14.3 milliliters and 1 atmosphere pressure. So we add some weight to the cup. Notice that inside this little gas of interest right here, okay, they've gone ahead and told you what the new pressure is. Okay, increase the pressure, okay, decrease the volume. And plotted there. Actually, though, instead of volume, the inverse of volume. Why? Because pressure is related directly to the inverse of volume. It's inversely related to volume, but it's directly related to the inverse of volume. So again now, adding to a total of 1,000 grams. Okay, notice that we have a higher pressure, a lower volume. Okay, now 1,500 grams, a higher pressure. Okay, a lower volume. Okay. Does that work for you? So that was Boyle's law. On to Charles' law. Okay, Charles looks at volume and temperature. And that's actually one of the pairs we didn't look at earlier. Okay, but if you keep the pressure constant, I bet you can imagine that if you're going to keep the pressure constant, for instance, if you increase the temperature, you're going to have to increase the volume. Does that make sense? You got to give it bouncing around room. Okay, so they are directly proportional to each other. Volume and temperature. And so here we go. I'll show you what we did a minute ago. If you have an equation like this, okay, with a proportionality symbol, you can replace that proportionality symbol with an equal sign. But you have to introduce a constant. It's funny how many constants there are in this universe. I just think it's interesting if we go to a different universe, are their constants going to be slightly different? I know I've heard that somewhere, maybe an elegant universe or something, okay? So if we rearrange for k, we have to what? Divide both sides by t to get k by itself? Okay, that's why k is equal to v over t. Just kind of an algebra sort of thing. The biggest problems I see when students work these sort of problems is that they don't rearrange correctly. All right. So here actually, and I'm like, now how do I describe this? Because I was looking at this in my office. It's the same set of experiments. Okay, let me kind of show you. The only difference between these two sets of experiments is what the temperature is along the x-axis. We're used to using Celsius, probably we're used to using degrees Fahrenheit if we talk about whatever the temperature is outside. Okay. So this is basically saying that, and there's 3 different systems, system A, system B, system C, that had different number of moles of gas, okay? But basically they behave the same, that if you take, as you increase the temperature, you increase the volume. That's why they have that kind of positive slope. So all this is showing you is that, for instance, in one scenario with one number of moles C, they said that this dot here is the same as this dot here. And I was like, are you sure? One of the things you're going to want to be able to do is to go back and forth between these two temperatures. And I'll kind of remind you down here that if you are given the Celsius temperature like that, degrees Celsius is equal to, and you want to convert to Kelvin because that's usually what you need to do. The Kelvin temperature, the new Kelvin temperature is equal to the degrees Celsius you have plus 273.15 units. That will be helpful. And here's why. Well, I don't know, here's why. But if we go ahead and focus just on Kelvin temperatures, we have a wonderful opportunity. All gas law problems are going to be worked with temperatures in units of Kelvin. What this says is as you lower the temperature on the Kelvin scale, remember that Kelvin has what we call an absolute zero temperature. Okay? As you lower the temperature, the volume will decrease. The volume decreases to what? 0 at 0 Kelvin. The problem is, and you probably already know this, or intuitively, around here, gases start behaving non-ideally. Non-ideal behavior. Gas behavior. Because we said that, I can't spell behavior. We said that in order for a gas to be behaving ideally, it doesn't care that there's any other particle there, no intermolecular bonds, and basically the size of the gas particle is 0. If you start, cooling it down, okay, that's not going to be the case. All right, so that's a lot about Charles' law. Probably more than you wanted to know or needed to know. So we have this cool XY intercept, actually, that happens if we make sure that we use temperature in terms of the Kelvin units instead of Celsius. Oh, I think this one's going to play for us. This one reminds me of what David Letterman used to do. He's retiring, right? What David Letterman, I think, used to do with regard to cooling things down and seeing what after you used liquid nitrogen to cool things down, seeing what cool things happen to those objects. So all this is showing you is Charles' law in that basically we have the balloons here. They are at room temperature, okay? And then, of course, this flask right here has something cold, liquid nitrogen, okay, only 77 units above absolute zero. And so obviously, as you cool it down, as you decrease temperature, you also decrease the volume. Okay, but they can reanimate when you just let them sit back up and let those little gas particles wake up. It's kind of like buying ants in the mail when, yeah. Have you ever bought ants in the mail? Yeah, I think they can send them kind of cold, and then when you heat them up, they go faster. Okay, so that was Charles' law. Avogadro's law, not so surprising, is related to moles. How volume and moles is related. And to me, this makes sense. As you increase, I usually think of as you increase the number of moles, holding pressure and temperature the same, you got to increase your volume. No buts about it, right? So again, we can replace the proportionality symbol with an equals and K, rearranging for K, and then K is going to be a constant for any given gas. And so it's equal to volume over number of moles. Okay, so volume and number of moles is directly related. And when we worked, when you guys balanced your chemical equations just the other day, right? You said a balanced equation is showing relative number of moles. And volume is related to moles. So guess what? You can, if you know a balanced equation, you can go with volume instead of moles with those stoichiometric coefficients. I know it sounds kind of strange, but I'll show you. Maybe. That's a good sign. So this is actually just assembling water molecules. So the little cute little white things, of course, are hydrogen, H2, and then the red things are O2, and we're going to make H2O.
Quantity and volume are directly related. If we take 8 molecules of H2 and combine them with 4 molecules of O2, we get 12 molecules and a combined volume. If we then react the mixture, we end up with 8 molecules of gaseous H2O, which occupies the same volume as 8 molecules of any other gas.
So this is all assuming that you are going to allow your volume to kind of expand and contract as it needs to keep the same pressure, constant pressure, okay? So just kind of gauging those circles, can you see where this circle over here is equal to size and volume to this circle right here? If you were to go ahead and see if this will let me do this, if you were to write the balanced equation of what this reaction is, you guys would say, let's see, how do I say H2? I'd say one mole of H2 plus 1/2 mole of O2 goes to form 1 mole of H2O. That's one way to look at it. Okay? So notice we take 1 volume of H2, 1/2 a volume of O2, and the volume we get of H2O, everything's in its gaseous state, no liquids over here. Okay, same pressure, same volume. Stoichiometric coefficients go along with the volumes. That's Avogadro's, that's a consequence, think about it, of Avogadro's law. Escape. Discard. Okay. So, and actually, how do I say this? There are some problems that you can rely on this and it can make your life, there's different ways to skin cats when it comes to gas law problems. And this actually can make your life easier if you use Avogadro's law, as long as pressure and temperature remain constant. You can relate volume right to moles. Okay, so we're not going to get to a problem slide, but before we leave, I want to show you how this works. How do we get PV is equal to nRT, and this is how we do it. Notice that we've talked about, what was that, Boyle's law, Charles' law, and Avogadro's law, all relate volume to something else. We can combine those volumes, okay, on the left side and combine the terms P, T, and N on the right side, and this is what we get. Then do you see we are just a 1 equals and constant sign away from where we need to be? Okay, so I said you can replace that proportionality symbol with an equal sign if you introduce a constant. So I put the K up there. It's about algebra, right? So if we want to, I think the next one you're going to see is rearranging it not to get K by itself. Maybe it is. To get K by itself, you'd have to basically, what, take both sides times P over NT. Does that make sense? P over NT times both sides to get K by itself. As it turns out, K actually is known as R. That generic K is really our ideal gas law constant. I feel like I'm at a commencement speech. So we are going to have to go, because I see we're already a little bit past. So no assignment slide. But if I had an assignment slide, it would be problems 27, 28, and so you don't need to do these, but I will, because if you're thinking, the only reason I would do this, if I was y'all, 27, 28, and 30, is depending upon what the end of your semester looks like, you actually have enough, and I'm going to go ahead and post my hints like I always do to these problems. These are not due Wednesday. Next time it's going to be Wednesday. Oh my God. Can you do? Yes. Will they be due Friday? Yes. Okay? So it's up to you. Happy Turkey Day. Go hug your kitties.